Okay, so let's continue talking about our properties of radicals and simplifying radical expressions. This time we have some variable expressions with our radicals, and what we're looking for when it comes to radicals is how do we reduce expressions that contain, well, powers that are not exactly the same as our index on the outside of this radical. Like I've got the cube root of negative 250 times x to the fifth and y to the seventh. Well, what we're looking for are perfect cube factors of each of these factors right here inside of the radical. And I know we've already talked about the idea of the number 250 as being 125 times 2, right? And so I'm going to carry my negative along with that. But I also have x to the fifth. Now what do I do with that? Are there any perfect cube factors? Well, the thing to remember is that when we have a higher power, we use our addition rule for exponents for exponents to divide up the polynomial. So we do actually have x cubed contained within x to the fifth if we remember that x to the fifth is the same thing as x cubed times x squared. And how about y to the seventh? Well, yes, y to the sixth times y. Now, why do we want y to the sixth? Well, y to the sixth is a perfect cube, right? It's a perfect cube of y squared, right? In fact, as long as the exponent is divisible by the index, we have a number that can be reduced. We would say that this is really the same thing as, if I separate off all my perfect cube factors, negative 125 times x cubed times y to the sixth and another cube root factor of 2 x squared and y. Now everything under this radical can be reduced, right? If you recall, all we were really doing in the last section was we were saying, well, if I had the cube root of y to the sixth, that's really the same thing as y to the 6 over 3 power, and that becomes y squared. Now I'm not going to have to repeat that each and every single time that I deal with an expression like this, but I can treat this as the cube root of negative 125, which is negative 5, the cube root of x cubed, which is just x, and the cube root of y to the sixth, which we've established is y to the second. And we're going to be multiplying that by the cube root of 2 times x squared times y under the radical. There's nothing else we can do to simplify that, and so we're done. There are no more perfect cube factors. All right, let's talk about this other one over here. We've got the fifth root of 128 x to the seventh. Well, 128 may not be particularly recognizable to you as a fifth root number. As a matter of fact, it's not a fifth root, but we would note that 128 is factorable, right? If we take off 2 goes into 128 64 times. 64, it's still maybe not recognizable, but how about this? What if we say it's 2 times 32? Is that recognizable to anybody? Well, hopefully you recognize that 32 is the same thing as 2 to the fifth power. So that's really, really helpful. We actually do have a fifth power factor right here of 32 times 4. So if I'm rewriting this second one, the way I'm going to rewrite it is that it's going to be a fifth root of 32, which is a perfect fifth power, times 4, times x to the seventh is the same thing as x to the fifth, times x to the second. Remember, it's always addition with exponents, and so we divide it up as x to the fifth times x to the second. And now we're going to take our perfect fifth power numbers, out of the fifth root. And this is going to become the fifth root of 32, which is 2, the fifth root of x to the fifth, which is x, and that will be multiplied by the fifth root of what's left over, and in this case that's 4 times x squared. Now nothing else can really be done to reduce this radicals because there are no more perfect fifth power factors underneath the radical, and so we're done. This would be considered simplified form for this radical expression. More to come in the next video.